Okay, so let us begin. Yeah, welcome to the final problem solving session for the course. So before I begin, I just wanted to say one thing, which is that um, a lot of the elements of the course um, is conceptual, and some of the elements of the course is computational. So what you might expect in your final exam would probably be a mix of some questions which are conceptual and some problems which are computational. You won't get all computational questions or vice versa. So, so my suggestion would be to, so whatever each of the concepts are there in the course, go through them well, understand them well, understand the key salient theorems, the key salient results that are there in the course, and and of course, you need to solve some problems as well. The level of difficulty of the problems would be kind of similar to the difficulty of problems that we have seen during the problem solving session. So it would not be too much different from that. All right. All right. So let's begin. Hope you can see the screen. So let us start off with. So one of the theorems that you would encounter is this divergence theorem. Okay. And so I'm going to assume by now that you understand terms like surfaces, volumes, hypersurfaces, vector fields, divergence, curl. These are some of the things that we have looked at over the during the course of the uh, of the problem solving sections. So I'll just state what this theorem is. So what this theorem basically tells you is that this is one of the versions of the theorem. There are multiple other versions of the theorem which if necessary I'll invoke, but not right now. So if you are in Rn and you have a vector field in Rn and you have a domain omega. So when we say a domain omega, uh, there is of course questions on what exactly do we mean by domains? What kind of domains do we allow? You can think of a domain as being like a um, as being an open set in Rn, where the boundary of the domain is a sort of a is a smooth Rn minus one manifold. Okay, so you can sort of think of this the boundary of the domain is to be a smooth or a piecewise smooth. Piecewise smooth um, Rn minus one submanifold. Okay. So what the divergence theorem basically tells you is that if you have this vector field x, so then divergence of x over omega is equal to integration over L omega x dot n cap. Okay. And what is n cap? So n cap is basically the outward facing normal. Okay. So I'll give you an example. Right. So let's say you are in R3 and you have the sphere in R3. Um, right. So you have the sphere in R3, which is given by the distance is equal to 1. This is your sphere. And let's say you have a vector field X, okay, and you want to do divergence of X within the region bounded by the sphere, which is going to be the disk. So this is your sphere, and you have the disk D3, which is norm of X is less than or equal to 1. Okay. And let's say you're doing divergence of X on this D3. Then this would be equal to the divert. You're supposed to take the integration over S2, then X dot N cap. So N cap is the outward facing normal. So you look at the region that you are right now currently. And of course, because the sphere is a two-sided surface, which means that uh, there is a notion of orientability on the sphere. So there's an outward facing normal and then there's an inward facing normal. Um, right. So you look at this outward facing normal, you look at the normal which is pointing outwards. Okay. And that is the direction of the normal in which you're supposed to take the inner product. This is the unit normal vector field on S2. Okay. Now, let's say you reversed this thing up, and uh, let's say uh, this is your disk in D3. This is your origin, and you have a vector field X, which is defined over R3. And let's say now you're doing divergence of X, not over D3, but you're doing it in the region outside D3. So you're doing it in the region of R3 minus D3. Okay. So this is the region in which you are, sorry. Um, so this is the region in which you are doing your integration. You're essentially excluding the disk. Okay. So now what happens is that you can again apply the divergence theorem. And according to the divergence theorem, you're going to do integration um, over S2, then X dot N cap. Okay. Now there's one crucial thing. So of course, this is not a bounded region. So you can assume over here that for this integral to make sense is that X vanishes at infinity. Okay. Like one way to sort of like one way to sort of like one sufficient condition for this to actually hold is that X is a compactly supported vector field. So I'm going to use, let's say, a notation. Maybe I'll use this notation vect C of Rn. This means that it's a compactly supported vector field, which means that outside a bounded region in Rn, X is equal to 0. Okay, this is what it basically means. If that holds, then you can again apply the divergence theorem. But now there is a catch. So because if let's say so your region is R3 minus D3, and R3 minus D3 has a boundary. The boundary of R3 minus D3 is again S2. But the outward facing normal is no longer this, but it's actually this. Okay. So when you were here, then the outward facing normal was in this direction. But when you are outside, then the outward facing normal is going to be in the opposite direction. Okay. So so you have to bear that in mind while doing the integral. So instead, this is not going to be n cap. Instead, you're actually going to be, this is going to go minus n cap. when you do the dot product. So I hope this is clear. Um, Now let's look at one problem. Problem is as follows. It's a straight application of the divergence theorem. So let S be let S in Rn be a closed two-sided hypersurface bounding a volume V. That is, L of Vs is equal to S. Say the area of S is equal to integration of divergence of X over Vs. Then what should be X? So this is the first question. I'll pause for a minute. I'll let you read the question. Um, and then if you have any ideas, you can discuss it with me. Okay, any ideas how to solve this? Okay. Since nobody is answering, let me solve the problem. Yeah, if you know the answer, then if you don't know the answer, then it's fine. If you know the answer, um, then do not hesitate uh, to share it, because then you know that what you're thinking is basically right. Okay, so let us answer the question. So what you have is a volume. Sorry. So what you have is a surface S, and there's a volume enclosing, which is enclosed by the surface S. Um, and so it's given that the area of S is equal to divergence of X. Then what should be X? Okay. So let us see what does the divergence theorem tell you. So divergence theorem tells you that divergence of X Vs is equal to X dot the n cap over the surface S. Okay. Now, if you want, now, of course, I hope you understand what these integrals mean. This is a volume integral. This is a surface integral. So if I write this a bit more carefully, so what this is divergence of X, and this is over a volume element in in Rn. Okay. So this is going to be basically equal to some dx1 up to dxn. Okay. So essentially so you're going to use the Lebesgue measure over Rn to compute this integral. Okay. This integral, on the other hand, is not the Lebesgue measure of Rn, but it is instead going to be over the Lebesgue measure of the surface S. Okay. And I discussed what that means in one of the uh, problem solving sessions. So this is x dot n cap, and this is over ds, okay, where ds is the Lebesgue measure over the surface S, and it is basically equal to the area of an infinitesimally small parallelogram that you can construct over the surface. Okay, but of course, but what is the area of the surface? So the area of the surface is basically defined as, is just defined as integration of ds over s. Okay. So for this to be actually equal to the area of the surface S, what we need is that x dot n cap is equal to 1. Okay. Therefore, so this is now is the question. Uh, so what I need is x is a vector field. So x is a vector field on Rn. Okay. Why do you need the vector field on Rn? Because you're going to compute, well, not necessarily on Rn, but you at least need the vector field to be defined on Vs, which is the volume enclosed by this surface. Um, so you need the vector field x to be defined on the volume enclosed by the surface, and the second point is that x, when restricted to the surface S, is actually equal to n cap. Okay. So the question is an extension problem. If I have a vector field which is defined on the surface, and it's defined on the surface as just the unit normal vector field. So let's say this is a vector field, 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 and so on. in order that I can express the area of the surface as a divergence of x, I need to be able to extend x. So let me just write it over here. X has to be extended to Vs. Okay. But the extension should satisfy this property, of course. Otherwise, it's not an extension, right? Now, the question is there any unique extension? So the answer is no. There isn't a unique extension of X. However, what the divergence theorem tells you is however you extend X, so even if you had like two extensions of X, so say uh, X and X tilde are extensions of the unit normal vector field NS. Let's call this NS. Then by the divergence theorem, the integral over divergence of X over Vs would actually be equal to the integral of divergence of X tilde over Vs, and that would be equal to the area of X. So of course, we have determined that there need not be a unique extension, but the question is, does there exist at least one extension? And the answer is yes, there exists an extension. So actually, there exists a non-unique extension of X, but there always exists an extension. Um, Now, what is the proof that that such an extension exists? Well, uh, I'm going to um, yeah, I mean, this can be a little bit tricky to prove that indeed an extension can be found out. Um, I mean, but I have to invoke one particular result, which is um, which is strictly not within the scope of the course. Right, and the idea is that there is something called a tubular neighborhood of the surface, and every surface has a tubular neighborhood. And and so I'm just going to write it briefly over here. An extension exists by virtue of a tubular neighborhood of S. Don't worry too much about this, but an extension exists, and so indeed, uh, so the question is a little bit ambiguous. I said what should be X. There is no one particular X. X X has to be an extension of the unit normal vector field on S. Okay. Okay. So I'll pause for a moment. Okay, let's proceed. Just give me one moment. Right. I mean, you don't necessarily have to um, um, well, yeah, I think you need a tubular neighborhood of S to be for this to be defined. But let's take an example. Okay. So let's say you have a sphere over here, and you have the unit normal field on the sphere, and let's say n is the unit normal field, and you want a vector field x such that x uh, so this is your surface S, which is basically uh, the unit sphere. So you want a vector field such that x on S is the unit normal on S. Okay. And okay, and how do you actually do it? Um, well, you can notice that. So what is the unit normal vector field on S? The unit normal vector field on X, S is just given by X by X cap. Okay. So this is N of S. So you need to be able to define this vector field um, on uh, over this volume enclosed by the sphere, which is just the disk. Okay. But you notice that this is not well defined at the origin. So at the origin, this is not well defined. So, but everywhere else outside the origin, it is well defined. So you have to make sure that you define the vector field in such a manner that that at the origin it becomes equal to 0. Okay. And the way you can do it is basically as follows. So this is a standard trick in calculus. We choose what is called a cutoff function. So let me just write it down. So a cutoff function. So a cutoff function is a smooth function, which is like this. Um, let's say rho is my cutoff function. So rho is a function um, which is 0, which at 0 is equal to 1, and at at 1 it is equal to 0. So it is some kind of a function which is like this. Okay. So rho is a smooth cutoff function which is supported on the interval 0, 1. So support of rho is within the interval 0, 1. And of course, rho is compactly supported. Well, not necessarily compactly supported, but rho of 1 is equal to 0. Okay. So now you can define a vector field xs, where xs is basically defined in this way. Um, so xs, sorry. So xs is a vector field on D3, on basically the unit disk. And xs is defined in this way. So xs, so if you pick a particular point over here, then xs of r of x can be defined as rho of 1 minus r times x by x. Okay. So where what is x? Where x is a point in S2, in S basically. So essentially what I've done is that if you take any particular point on X, then all the points that lie on this ray from the origin to X can be expressed in the form of R of X, where R is basically a scalar that runs from 0 to 1. Okay. Then the vector field at Rx is basically defined as rho of 1 minus r times x of 1 minus x. So, so I'm essentially using the cutoff function. Like alternatively, you could just express this formula in this way. This is an equivalent way to express it. So for any y in the disk, x x x at that point y is basically equal to rho of 1 minus mod y times y by mod y. Okay. So you notice that by the time you come to the origin, this rho of 1 minus y is equal to 0, because when you have the origin, then mod y is equal to 0, and rho of 1 minus and rho of 1 is already equal to 0. So you've essentially cut off that function by that time. Um, right. So this is then an extension of the vector field x. um, that you have extended it to uh, that you have extended it to the whole of the disk. And if you take this vector field, so essentially what my theorem tells you is that now if I do divergence of rho of 1 minus mod y times y by mod y, if I do divergence of this guy over the unit disk, then I will basically get the surface area of the unit sphere. Okay. So I hope you uh, understood the problem. I'll pause for a moment and let you, if you have any questions, you can ask me. Then we can move on to another problem. You can obviously see that the extension is not unique, right? If you could have chosen another cutoff function which could look like something like this. So it would have been a cutoff function at half and zero, and let's say you had another cutoff function rho prime. Then rho prime uh, would also have given you the area the of the unit sphere. Okay. So it's very interesting that you have a result on an integration where the value of the integrand, uh, or rather the um, yeah, I mean rather this is independent of the choice of um, right. So this is independent of how you do the extension. Okay. So it's an interesting result. It's an elegant result. Okay. So I guess this is clear then. So let's move on to another problem. This problem is from the textbook by Krasik. So I'm just going to copy the problem. Um, yeah, if you do not understand it, if you do not understand something, this is the last class effectively. So feel free to ask me. Okay. So I hope you can see the problem. I'll pause for a moment and I'll let you read the problem. Yeah, I'll just come back within a minute. In the meantime, you can think about the problem. All right. So let's um, were you able to understand the problem? Okay. So let me just clarify a few things. So when we say that a function is harmonic, that means the Laplacian is equal to zero. Harmonic function implies that the Laplacian is equal to zero. So that's number one. And the second is you see this symbol del G upon del N. You may wonder what this means. So what this means is that so del G upon del N is basically equal to the gradient of G and you take the inner product with N. Okay. So that is basically equal to del G upon del N. So why is it called del G upon del N? It is basically uh, how much the function varies, um, how much the function varies along the normal to a surface. So let's say you have a surface S, and this is your unit normal and cap. Then del G upon del N is basically how the function is varying across the norm. That is your del G upon del N is basically equal to ddt d upon dt at t equals to 0 of G of T n cap. Okay? That is your del G upon del N. Now, let us solve the problem. Again, this is an application of the divergence theorem. So let us first establish a few. Uh, let us first establish a few identities. So let f and g be two functions. F and g are, let's say, they are two C2 functions. So then you know by the divergence theorem, the divergence of f of grad of g is equal to divergence of f comma divergence of g. This is the inner product plus f of divergence of grad of g. Okay. Sorry, there's no bracket here. Plus f of divergence of grad of g. But divergence of grad of g is precisely the definition of the Laplacian. So this is just equal to f of Laplacian of g. Okay. Now let us integrate. Let's say you have a, so essentially what is given is that you have a region T. So there is a region T and it is bounded by a surface S. So let us integrate. So divergence of f of grad of g over the region T. That is equal to grad of f comma grad of g integral over T plus f of Laplacian of g over T. Okay. However, it is given that g is a harmonic function, and so Laplacian of g is equal to 0. So this term, of course, drops to 0, and you are left with integral over T f of grad of, sorry, not f of grad of, so sorry. This is divergence of f of grad. So divergence of grad of g is equal to integration over T grad of f comma grad of g. Okay. Now apply the Stokes theorem. So divergence of so this term is equal to integration over S f of grad of g times the unit normal vector ds. Okay. So we have arrived at this result. And now for the first part of the problem, this is the first part of the problem. If you set f equals to g, then um, what you get is integration over s g times grad of g dot n cap is del g upon del n ds. And over here, grad of f and grad of g are the same. So you get the norm of grad of g squared over t. Okay. So this is your first identity. The second identity is very interesting. Um, so the second identity states that if this function was such that the function the the function is essentially um, constant in the normal direction of s. Okay, then g is constant in t. Okay, I mean the result just follows from n, because if del g upon del n is equal to 0, then that means that integral of grad g squared is equal to 0. But of course, this is a positive quantity, so the integration of a positive quantity can be 0 if and only if. So this is if and only if grad of g is equal to 0 on t, which means that g is a constant. Okay, so this is an interesting result for sure. Um, Now let's look at the third part. Okay, so how do we solve the third part? Well, we have established from this formula star that integral over f of grad of g times this grad of g inner product with this unit normal is equal to del g upon del n. So we have established that this is equal to the inner product over t of grad of f comma grad of g, right? Now, if you interchange f and g, so interchange f and g, you get g of del f upon del n times ds is equal to integration of grad of g times grad of f. Okay, which is just the same as this thing. And therefore, we get the identity. Okay, of course, all these identities hold true only if f and g are harmonic. Okay, if f and g are not harmonic, you will see some additional terms. Uh, all right, so let's look at the this part D. So the part D is again. Um, so if del f upon del n is equal to del g upon del n, then that just basically means that del upon del n of f minus g is equal to 0, right? Also notice that if f and g are harmonic, then f minus g is also harmonic. So Laplacian of f minus g is equal to Laplacian of f minus Laplacian of g, which is 0. And so we established in this formula, which is from B. So from B, f minus g is a constant. Okay, so that answers part D. And now you're left with the final part, which is E. Okay. Now, what is the okay? So, what is the Laplacian? Let's look at the final part. So, the Laplacian of f is equal to the divergence of grad of f, right? So now um, what the divergence theorem tells me is integration over the volume T of divergence of grad of f is equal to integration over S grad of f times the unit normal vector ds, which is just del f upon del m. Okay. Um, Now, of course, this is a scalar quantity, and because the function f is C2, so this divergence of grad of f, this quantity in itself, um, or rather this integral, sorry, is kind of uh, so this quantity will basically tend towards so if you fix a particular point, so say P is a point in the domain of F. So this quantity would basically tend towards the divergence of grad of F times the volume of T as and this is only a um, I mean this is only a rough statement. This is not a mathematically precise statement. As the volume or basically as the region T collapses on P. So essentially what this means is that let's say you have a region T and you have this point P, then as if you constantly shrunk uh, if you constantly shrunk this region and made it basically tend towards P, then of course this is what you get. And so basically you can write the divergence of grad of f at this particular point P as basically this limit term. Okay. I'll pause for a brief moment. If you have any questions, you can ask me. I'll pause for a moment. So, for instance, if you um, so a concrete example of this would be like, let's say your T was a small disk around P, and you let the so the idea is that say T is the R disk around P. So basically, what this means is that T is equal to D of P comma R. So that's all points X such that X minus P is less than or equal to R. So then you can essentially restate this theorem as the Laplacian of f at P is equal to limit R tending to 0 um, 1 by 1 by volume of the R disk. Volume of the R disk, we can write it like this. times the integration over right times the integration over the boundary of this disk, which is, let's call it S of p comma r, and then del f upon del n is basically grad of f dot product with the unit normal vector field, and the unit normal vector field is basically given by x minus p divided by norm of x minus p, which is just equal to r. Okay. So this is how we can then restate this result. If it was a disk. Okay. Okay. Hoping things are clear. Let's let's look at some other problems. Right. So I mean, how does the divergence theorem help us? The divergence theorem helps us because it essentially lets you. So what is the advantage of this divergence theorem? So of course you get to prove results, but that's also important. But what it does is that it it is a computationally efficient way of doing things, right? Because it essentially translates a problem of doing an integration over a surface um, where um, where it may be difficult to do the integration on the surface because in order to do an integration over the surface, we have discussed this in one of the previous problem solving sessions. You need to be able to partition the surface into parts where each part can be represented in some way as the graph of a function and so on. And this is tricky. And then of course you have to take the Jacobian of such a map and then uh, uh, basically basically compute a uh, basically compute a unit area element for that surface and so on. So it makes it a somewhat complicated process. Whereas if you do the integration a um, for a um, for a region in R3, then you can simply use the Lebesgue measure on R3, dx, dy, dz, and so on it makes the integration easier. It is easier to determine what the measure to be used on the integral is. As for the surface, it's tricky. Okay. So if you take one example like this, let's say you pick this one. So you're given a vector field F, which is given by x plus y squared, y plus z squared, and z plus x squared. And you are basically given this ellipsoid, which is x squared by a squared plus y squared by b squared plus z squared by c squared is equal to 1. And you have to do f dot n cap over this ellipsoid. Now it's considerably tricky to do the integral over the ellipsoid because, well, for one, you know what the unit normal vector field is. Uh, I mean, that in itself is a little bit tricky to compute what the unit normal vector field is. But it's also what is also kind of tricky is what is this ds term over there. And we discussed this before, how to essentially get the Lebesgue measure corresponding to this. Um, Maybe you recall it, but I'm not going to go into it right now. Let's instead you can just try to use the divergence theorem, which is integration of Vs. This is the volume bounded by S, divergence of F, and then you can use dx, dy, dz. Okay. Right. So now the advantage is that if you can appropriately set the limit. So this is just equal to um, you have like an ellipsoid like this. So this would become, so your x would vary from minus a to a, y would vary from square root of minus of 1 minus x squared by a squared to 1 minus x squared by a squared. And eventually z would vary from square root of 1 minus x squared by a squared minus y squared by b squared minus, and then you compute the divergence of x, which is something you can do, which is so divergence of f is equal to del x of f1 plus del y of f2 plus del z of f3 which is 1 plus del y of f2 is also 1, and this is 1. So this is equal to 3 times, um, so this is 3 times d dz dy dx. And if we just write it down, then this is just equal to 3 times the volume of this ellipsoid. Volume of the ellipsoid. Okay. So yeah, I mean, this is how the divergence theorem basically uh, helps you. Okay, just give me a moment. Okay. I hope things are clear. Okay, let me look at some more problems. Okay. I'm not able to find some problems. Let me see. Okay, let us look at this problem. Since I'm not able to find problems, let us look at this problem. Going over to a different topic, which is complex analysis. Right. Find the residue of this function f(z) at z equals to 1. Okay. Um, so what is the residue of a function? So if you look at the function over here, which is fz, then the function fz um, has a single singularity, which is at z equals to 1, and you have a pole of order 2 at z equals to 1. So uh, the definition of recall the definition of singularity. If you have a function which looks so if you do a Lorentz series expansion around that singularity, so if you do f of z minus z naught, to get like a Lorentz series expansion. And because it's a uh, and because it's an order 2 right. So you get some expansion of the form sum over of am z to the power m, where a m is from minus infinity to infinity. But of course, you have a pole of order 2 over here. And because you have a pole of order 2 over here, so your the number of negative terms that you will have is at most a minus 1 and a minus 2. Right. And so the residue of f is just equal to a of minus 1. Okay. So we have to basically compute a of minus 1. So you need to do a Lorentz series expansion at z equals to 1 and then compute a of minus 1. So, of course, you can do a Lorenz's expansion in a standard brute force way, but there is a sort of easier way to do the computation. So, notice that you write this fz as a product of two functions. So, one is gz times z minus divided by z minus 1 squared. Okay, where this gz is equal to z squared by z plus 1. Now, of course, g is a holomorphic function at z equals to 1. So, say you can write this gz. Let's say, so you can do like an analytic expansion of g around z equals to 1. And that would look something like b0 plus b1 of z minus 1 plus b2 of, sorry, plus b2 of z minus 1 squared plus dot dot dot. So when you do fz is equal to gz by z minus 1 squared, that would be equal to b0 by z minus 1 squared plus b1 by z minus 1 plus b2 and so on. So the term which has a power of minus 1 would be basically b1. Therefore, the residue of f at z equals to 1 is basically going to be equal to b1. Okay. So all it suffices for us is to compute b1. So we need to basically do an analytic expansion around z equals to 1 for this function g. So let's do that. So we write, so gz is equal to z squared by z plus 1. So that is equal to z. So that is equal to z minus 1 squared plus 1 plus 2 times z minus 1. And here you write this z as equal to z minus 1 plus 2. So you write this as in this way. Put a half over here. Write this is equal to 2 times 1 plus half times z minus 1. Okay. Now let us do the expansion as usual. So you get 1 plus 2 times z minus 1 plus z minus 1 squared by 2 times right. So if you just write this thing out, you will get that this is equal to 1 plus 3 by 4 times z minus 1, and plus there will be higher terms of z minus 1 squared. So this b1 term that we got, so this b1 is equal to 3 by 4. Okay? And so the residue of f at z equals to 1 is equal to 3 by 4. Okay? Right. So I hope you got the problem. Now let's do this problem. Um, right. So if you look at the circle which is centered at one of radius one, then basically you notice that there is a single. If you look at the region bounded by the circle, then it has a single singularity um, which is basically at z equals to one. Because the other singularity, which occurs at z equals to minus one, lies outside the circle, right? And so by the residue formula, what you get is that the integral of f is equal to 2 pi I times the residue of f at z equals to 1. We computed the residue of f before. So that is just equal to um, 3 pi I by 2. Okay? So this is how you can sort of compute these integrals. So in general, if you have like multiple residues, you need to add up. In general, if you have like multiple singularities, you need to add up. Uh, you need to add those up basically. Okay, I'll give you one example. Okay, let us look at this problem. So basically, the idea is as follows. If you have, so let me just write down the residue formula. Maybe you know this already, but let's just write it down. So the residue formula basically tells you that um, if you have a function f and you have this closed curve gamma, where f has some poles within this gamma, then integration of f, sorry, then integration of f along gamma is equal to 2 pi I times these. Let's call these poles as Z1, Z2, and so on. And then you have the summation over residue of F at each of these poles, Zi. Okay. I just realized I used I for both this. So let's just write as 2 pi square root of minus. Okay. Now there's one more thing. So you have to check something called the winding number of the curve. So the winding number is how many times does that curve loop around that particular point? Okay. Um, so and there's also this term which is W of F comma ZI. And this is the winding number of actually I wrote F, it's actually gamma. Winding number of gamma for Zi. So essentially, this counts the number of times the curve loops around that particular point Zi. So for simple cases, you're going to have the winding number to be equal to one. But let's say uh, an example. Let's say you have you have a point over here, and you have a circle. So you can, let's say you traverse the circle once, and then let's say you traverse the circle two times. Okay. So that would be an example of so let's say you let gamma to be the unit circle, right? Uh, and now let's say you traverse the circle twice, so you go with a velocity of twice. So let's say you use this curve gamma of 2t, right? Uh, so gamma of 2t would have a winding number of 2. And gamma of t, whatever the winding number of gamma was, gamma of 2t would have a winding number of twice of that. Because you're looping around that point two times. Okay. Um, so let's solve this problem. Let fz equals z squared minus 2z plus 3. Then what is compute this quantity? C of 1 by fz z, where what is C? Where C is the rectangle, where C is basically the rectangle bounding minus 2 comma 2 cross 2 comma 2 minus 2 cross 2. So let us compute the roots of fz first, because it's 1 by fz and it's a quadratic equation. So the roots of fz uh, turn out to be equal to 2 plus minus 8 by 2, which is 1 plus minus root 2. Okay. So now if you plot this rectangle, so you end up getting two roots. So one root z1 is over here, which is 1 plus root 2j, 1 plus root 2j, and you have another one z2, which is 1 minus root 2j. Okay. And you have to, this is, let's say, uh, your curves. Okay. Right. So if you write down if you consider this function, which is 1 by um, 1 by z minus z1 times z minus z2, then this guy is equal to 1 by z2 minus z1 times 1 by z minus z2 minus 1 by z minus z1. Now you have to compute the residue of this function at z equals to z1 and z equals to z2, right? So when you are at z equals to z2, so then notice that this part, which is 1 by z minus z1, that is basically the function is analytic in a small region around z equals to z2, right? Uh, so near near z2, the residue of f at z2 is equal to 1 by z2 minus z1, and near z1, the residue of f at z1, well, what is that? So at z1, this part of the function, which is 1 by z minus z2, is holomorphic. So you ignore that, and you're left with just this part of the function. So the residue is actually equal to um, minus of 1 by z2 minus z1. And so if you perform the integration, so if we call this as f, sorry, not f. So then integral of 1 by fz is basically equal to um, the residue of actually I wrote it as f. I should write it as 1 by f. Is equal to the residue of 1 by f at z1 plus the residue of 1 by f at z2. Here it should be 1 by 2 pi square root of minus 1. And this is equal to 0. Okay. So the integral is equal to 0. So I hope you got how to apply the calculus of residues to compute these integrals where the domains have poles in them. Okay. So this is the last problem that I was looking at for the day. Um, I'll pause for a moment. If you have any questions, you can ask me. Um, Effectively, this is the last class. So if you have any questions or any general thoughts, you can let me know. Okay, if you have any general thoughts or um, if you have any questions, let me know. Um, this is effectively our last tutorial. Were you able to find the course interesting? Were you able to learn some things from the course? Were the tutorial sessions helpful?